Okay. So we are going to discuss the few concepts on soil productivity, as the chair said this morning. So the first concept we wanted to discuss now is the concept of soil fertility and productivity. And before we go into the concept of soil fertility, we need to understand what is soil. Soil is defined differently by different users. If you look at the first definition we have put, that it's a layer of material that cover the land, that could be a category of geologists will actually take it that way. For those one who are doing cropping, they will actually think that is an area where plants are anchored and grow. Of course, the geologist will say this is made of weathered rock, decomposing plant and animal materials. But so close to physicists will actually think that is space for air and water movement. But all this in mind is basically for production purposes. Layers look like, you can actually see, and those layers is what we the top and subsoil. You actually, each of those layers has different types. So now let's go to the concept of soil productivity. Productivity is defined as the capacity of the soil to produce specific crop yield under specified environmental conditions and management. It is defined in terms of physical, chemical, and biological properties which favor plant growth. While soil fertility is the capacity of the soil to supply plant nutrients in adequate amount and suitable proportion without toxic element. By looking at the two definitions, we can actually observe that it's not mandatory that when you have a high productive, where you have a productive soil, it actually means the soil is fertile. But a highly productive soil should be fertile. You can have a very fertile soil with low productivity because of those environmental conditions and management of the soil. So fertility can be inherent, but it can also be acquired. Inherent, it actually mean naturally with the properties. With each property, the soil is rich in nutrients, the essential nutrient for plant growth. Those one who are the soil which have acquired soil fertility, it actually means that we have in one way or the other. So the essential elements are basically macronutrients are those nutrients which are required in big quantities. That is nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. And then you have those elements which are needed in small quantities like iron, manganese, copper, zinc, boron, molybdenum, chloride, and then nickel. But among the key elements for plant growth, we still need carbon. Which can be translated into organic matter, and which we know is a good store of nutrient. Then you need, of course, water, element of water, and that is hydrogen and oxygen. So, but we also have some elements which are not essential, which may be needed but not essential. And most of these, unfortunately, like lead, cadmium, mercury, may not be very, very useful for the plant. So soil fertility can be lost in different ways. It can be lost by losing the nutrient. It can be lost by erosion. That's one way of losing the nutrient. It can be excavation. When you excavate a given land, may not be having the same fertility as uh, oh, now I'm in problems here. So as I said, you have different aspects to consider when you are looking at parameters which can affect productivity. So you can have issues of management, you can have issues of climate, the soil type, and if there is any incidence of pests and diseases, all those will affect production. Yeah, so now in terms of productivity of an ecosystem, so you can have productivity at land level, but you can also have this at the landscape level, but you can also consider it for any ecosystem. So the productivity of ecosystems will be based on availability of light, the type of soil, precipitation, temperature, of course, and the nutrient availability. So it is here defined as the quantity of biomass produced each year on a given area. And this can be in gigagram or gram per meter squared. So, and this productivity depends on the global energy budget, which influence on one way or the other the photosynthesis. Can we go to the next slide, please? The more the crop transpires, the better for the productivity of the ecosystem. So, and then we can define, just go back, we can define the net productivity and the compared to the global productivity, which is based on the amount, the total amount of nutrient someone obtain, and the net primary productivity, which is basically what is available to the consumers. So a different ecosystem will have different NPP. A grassland, productivity on a grassland is going to be different from productivity on a banana or a coffee or annual crops or even in the forest. So how do we estimate soil productivity? So the other one was more of land productivity, but this one now is soil productivity. So soil productivity can be evaluated directly or indirectly. The direct evaluation is actually mean that we have some field assessment, and we can actually do testing of this in laboratory using simulating some climatic and management conditions. But indirect evaluation will consist basically on modeling these ecosystems. So for direct measurement, you have a number of parameters to consider. And these parameters can be put in a model. And the most important model so far developed is the Modified Soil Productivity Index and the Land Productivity Index, which uses a number of parameters depending on the data you have. For this particular model, we have the cation exchange capacity, we have the soil depth, the base saturation and pH, we have organic matter, slope, texture, drainage, and the gravel content that we have used in this particular model. Now, for each of these parameters, we have the threshold. We have the threshold, so we can have a low, moderate, good, and very good according to for different parameters. And we have tried to look through the different through the literature, what people would call low in terms of CAC, cation exchange capacity, and what people would call low for base saturation, or what people would call low for depth. For every parameters we had, we looked for the different threshold to be able to put some of these parameters in a given class. So that's for soil productivity. Now, for above ground productivity, especially what we call the vegetative biomass, we have a number of models existing which can assist to actually make an estimation of this. And some of those are using allometry and allometric equations. These are power functions where biomass is expressed as a function of different variables. In some cases, maybe the height or maybe the diameter of the trees, but also it can actually come from the basal or the canopy coverage. Some of these functions can just be done at plot level, at landscape level, or it can even be at catchment level. So we have we can do this estimation at different scale. As I said, you can do it at plot level, you can do it at landscape level, you can do it at micro catchment level, you can do it at catchment level. The accuracy, of course, will be diluted as you move from plot to catchment. Alvin, can you move down? Okay, so the different ways, there are different ways of capturing this information. So we can get it by looking at the plot, doing measurement at plot level, but we can also do it by looking at it from above the surface using remote sensing features. So in this case, once we can actually do it using geostatistics. So if we're looking at remote sensing level, then we need to bring parameters which will characterize the features from above. And this one of the most importantly used parameter is the normalized difference vegetation index, what we call NDVI. So this is basically a polarized fraction which deal with the red and the near infrared reflectances. When you talk about polarized, so I was talking about the NDVI and the biomass. So a very strong correlation models, very strong correlation have been observed between the biomass and NDVI. And some have also developed power functions or exponential functions between the NDVI and the biomass. The next slide show that correlation and fitness. So you can see from the Next slide. From this slide, that you can use either a natural log function, a linear function, an exponential function, or a power function to estimate biomass based on the NDVI. So the second part of this introduction is to take you through the modeling aspect based on what I've presented now. So I've presented how biomass could be assessed. Okay, so the soil productivity aspect, as I said, we had, so basically as I said, we have a number of parameters and we have developed the different ranges for each parameter. So we go to the cation exchange capacity. If you look at the cation exchange capacity, you will see the diagnostic, the classes we had. So we had for low, moderate, high, and very high, but also we had the cutoff values. And then we have what we call the rating factors. So we brought in an if condition to make sure that we can actually, from our soil data, know which region has low, moderate, high, or very high cation exchange capacity. So based on those factor rating. Next slide, please. So this was done for all the parameters. So if you take organic matter, you do the same. So very low for us was less than 1%, and we gave it a rating factor according to literature 2020 as a rating factor. And then low 50, moderate 70, good 85, and very good 100. And then we could develop a layer of soil organic matter based on that. And we did it for all the different parameters for which we could actually get data for the region. Now, the issue now was to combine. So we needed now to combine all these parameters to get what we could call the soil productivity index. Now, we had two models, and we tried to put two more models to make sure that we could select the best model and see which one was bringing us more errors compared to the other, and which one was more accurate compared to the other. And it came up that the soil productivity index turned out to be better for most of the regions we had. So, and that's what we actually use and put in QGIS, using the facilities in QGIS to actually develop a tool which could estimate for us soil productivity. So then once we had all these layers put together, when we had all these layers put together, then we combined them in land productivity index. And using the formula in bullet 3 as 100 times the square root of the product of the different factor rating. If we had one factor rating, then we'll divide by 100. If you had two factor rating, we divide by 10,000. If you have three, it will be 1 million. So every time is 10 power 2. And then the product was again sliced into very low productivity using the classification which exists in literature. So very low was less than 30%, low was 30 to 50, moderate was above 50 to 70, high was above 70 to 85, and very high was above 85. So 85 to 100. So that is what was done in terms of soil productivity. Now, in terms of biomass, so we had two models here. We had the model which is based on the NDVI, which assists us to get an indication of the above ground productivity, but also we had the land productivity index, which was assisting us to get soil productivity index. So the NDVI, the land productivity index, let's say the above ground productivity index was basically based on the NDVI, which of the region, and getting their reflectances, and then detrending them, because these images had an effect. The rainfall was influencing more of the type of vegetation and the vigor of vegetation. So we needed to detrend the effect of rainfall on this NDVI so that we know what exists as NDVI without rainfall effect. And then that one was classified to get the above ground productivity index. Now, for soil productivity, of course, we had a nutrient aspect in it, that is nutrient, organic matter, texture, gravel, and moisture availability, which were considered. But in addition to that, we had to look at what type of fertilizer is the amount of fertilizer which is added in the system. And we, as I said, we had the two models to consider here. We had the above ground productivity model, and then we had the soil productivity index. Productivity, we had nutrients, organic matter, texture, gravel, moisture availability on terms of soil, but also had to consider the aspect of fertilizer. We also had to consider the aspect of soil, and also the aspect of human factors. So by combining nutrient, organic matter, texture, we didn't combine the two, but we came up with different assumptions based on what our own experience in the region. And that brought us to have the two models, because you can actually have a very nice soil with very high productivity, but with low above ground productivity.